4.5, solving polynomial equations. I'd like to find the solutions to a polynomial equation and the zeros of polynomial functions. This would be in a graph. On the graph, these would be the zeros where it crosses the x-axis. And secondly, using the rational root theorem. So when you get a problem like this, the question is to solve for x. In other words, try to factor it and solve for x. You can see that 2x is the greatest common factor. When you undistribute, this times this gives you what's above it, and that's 6x plus 6 is equal to, actually plus 9 is equal to 0. So in this case, you're going to see that it's going to be x minus 3 and x minus 3. Again, distributing through and checking that middle term, negative 3x, negative 3x, negative 6x. That tells you a lot. Now, the answers are where you put each of these equal to 0. So you're going to see that x is equal to 0 and x equals 3. There are two solutions here. It's a double solution, which means that there are actually two x-intercepts at 3. And so if I want to graph this, what I want to do is put in my x-intercepts, but at 3 realize that instead of going through 3, it's going to bounce off of 3. And that's true because when you put in a number to the right of 3 or just the left of 3, when you multiply it to each other, you're going to get a positive number. Or if we're on the other side, you get a both negative number or positive number. Regardless, you're going to see that it's going to bounce off of that 3. So that we know is true. And I also see that it's going to have x cubed and it's positive. So I know that the graph has got to come something like this. So that tells me that it's going to come down and then it's going to go back up. And then at 3, it's going to bounce off of 3 and head up. So you would know that this graph would look like that graph. It's a positive cubic graph bouncing off of 3 because of the double root. Now, let's say, for example, in this problem, you cannot factor it. If you can't factor it, then we want to use the rational root theorem. If can't factor, use the rational root theorem. And what you're doing is you're looking at the potential rational factors, the possible rational factors. In fact, it's saying that all the rational factors will be the ratio of the factors of a sub 0 over the factors of a sub n. And that's what this is looking at. So you're really only looking at the first coefficient and the last constant here. So what does that mean? That means in this problem, if I went to go to factor it, you wouldn't be able to, so now you're stuck. So then you've got to apply this P over Q. Now, P over Q is equal to the possible rational solutions. And I'm looking at the coefficient of this first term, and I'm also looking at this constant. The possible rational solutions are going to be the factors of 24 over the factors of 1. Now, this is a long list, and they can be very, very long. But because it could be plus or minus, it's going to be plus or minus 1 over 1. I'm thinking about all the factors of 24. 1 only has 1 as a factor, so it's going to be plus or minus 2 over 1, plus or minus 3 over 1, 4 over 1, 6 over 1, 8 over 1, and 12 over 1 and 24 over 1. All of these, plus or minus 1, plus or minus 2, these are all possible answers, all possible solutions, rational solutions to this equation. So now you've got to figure out, well, which ones are the rational solutions. Now, I'm going to say that you could do synthetic division and find out where the remainder is 0, but to me, it's a little bit easier when you think about this in terms of a table because of the 0 factor test. If you plug these numbers in for your x, and if you get 0 as your f of x, then you know that that is going to be a factor. So if I plug one in, and this is easier, in my opinion, than the synthetic division. But if I put 1 in, I'm just going to get 1, -5, -2, and 24. And when I add those up, it is not going to give me 0. I don't care what it does give me. I just care if it's 0 or not. -1, as I put in and add them up, you're going to see that that does not give you 0. 2, 8, let's see, that's going to be -20, -4, and 24. That is a no. And the last one, -2, is, let's see, -20, 4, and 24, and that one is a yes. So x minus 2 is, or x plus 2 is really a factor. That means that I can use synthetic division now to get my other factors. So let's see. First of all, I want to make sure that this is correct. This is -2, and then I'm going to put the coefficients up here. And remember to carry this down, multiply and add. Multiply and add. Multiply and add, and let's see, where did I make a mistake? -2. Whoops, there's my mistake right there. This is +14, so this is 12, and then this is -24. Hopefully you caught that before I did. If so, that'd be a good sign. That tells me that x squared minus 7x plus 12, which is this right here, that's my remaining polynomial, can also equal to 0. And you can see that when you factor this, you get -3 minus 4, -3x minus 4x is -7x. Okay, so all this means that the real solutions are going to be x is equal to -2, x is equal to 3, and x is equal to 4. I got -2 from this, or from this, and I got -3, +3 and +4 from solving that. Now, if the question says just list the rational solutions, the answer would be right here. You would stop at that point. If the question is find all real solutions, then you would go ahead and do these numbers, positive -1, positive -2. One of those is going to give you P over Q in the problems that I give you. Now, if, for example, you get one answer, 0 using P over Q, at that point, you can use synthetic division to get this equation. But it's possible that this may not be factorable. Now, if that's the case, then use your graphing calculator and get the other zeros. So once you go through the method and get one answer, I'm saying, hey, that's good enough. You know how to do it. Now go grab your graphing calculator and get the other ones. And again, the ones you want to test are 1, -1, 2, and -2 in this particular P over Q.